Have you ever stopped to wonder how doctors can see deep inside your body, mapping out your brain or spine in incredible detail without ever making a single cut? Well, today we're going to pull back the curtain on one of medicine's most powerful inventions, magnetic resonance imaging. We're going to break down exactly how this technology turns some pretty fundamental physics into images that literally save lives. So, how does it all work? Let's dive in.
At its heart, MRI is all about creating this unbelievably detailed map of the body's soft tissues. And what you're looking at here is a real MRI scan. It just shows the power of this technology, doesn't it? The ability to capture something so delicate with such stunning clarity. This is the level of detail we can get, peering deep inside ourselves, all without a single incision. It's all thanks to a really clever use of magnetism and radio waves.
All right, so to really get this, we're going to go on a clear journey. First, we'll hop in a time machine and see how MRI was even discovered. Then, we're going to shrink down to the atomic level to meet the star of our show, the proton. From there, we'll uncover the three-step process the scanner uses to get a signal. Then we'll explore the absolutely crucial concepts of T1 and T2 relaxation. And finally, we'll see how it all comes together to create these powerful diagnostic images. Okay, let's kick things off with Section 1, our introduction to MRI. We'll trace its path from this pure physics idea all the way to the indispensable tool it is in clinics today. You know, the story doesn't start in a hospital, it actually starts in a physics lab. Back in 1947, two physicists, Felix Bloch and Edward Mills Purcell, independently discovered the fundamental principle of magnetic resonance. But get this, it then took 3 full decades of brilliant engineering before that principle was finally harnessed to produce the very first clinical MRI images in 1977. And that discovery, it changed medicine forever.
So how do you get from a physics principle to a medical marvel? Well, the answer is in Section 2, the physics of the proton. To understand MRI, you have to understand the tiny, tiny magnets that are inside every single one of us.
The whole reason MRI works so well on us is because our bodies are mostly water, H2O, and that means we're packed with hydrogen atoms. The nucleus of a hydrogen atom is super simple. It's just one proton. And this little proton has two properties that are the absolute key to MRI. It has a positive electrical charge, and it has this built-in property called spin. Just think of spin like a tiny, tiny top that's always spinning. It never stops.
So, how do those two things, charge and spin, make a proton act like a magnet? Well, it's actually a pretty straightforward chain of events. First, the proton is constantly spinning on its axis. And, since the spinning particle also has a positive charge, its movement creates this tiny little circulating electrical current. And, as you might remember from basic physics, any moving electrical current generates its own magnetic field. The end result? Every single hydrogen proton in your body is acting like a microscopic magnet. Now, this slide shows a really important idea. On the left, you see a single proton, behaving like a little gyroscope with its own north and south pole. But on the right, that's the reality inside our bodies normally. We have billions and billions of these little proton magnets, and they're all pointing in completely random directions. Their magnetic fields are all over the place, effectively canceling each other out. This chaos, this is the baseline state. It's the before picture that MRI is about to completely change.
So the big question is, how do we go from this chaotic swarm of tiny magnets to a beautifully detailed image of the brain? The answer is in Section 3, the three-step MRI process. It's this really clever way of lining up the protons, knocking them over, and then listening very carefully to the signals they send back. The whole process really boils down to 3 key steps. First, alignment, where we use a huge magnet to bring order to the chaos. Second, excitation, where we deliberately knock them out of that new order with a pulse of energy. And third, and this is the most important part, relaxation, where we just listen as the protons give off that energy, creating a signal we can actually detect.
Okay, let's break down Step 1, alignment. When you slide into an MRI scanner, you're being placed inside an incredibly powerful magnetic field. Think about it like this. Imagine you have 1,000 tiny compasses all pointing in random directions. The moment you bring a big magnet nearby, what happens? They all snap into alignment, pointing north. That is exactly what happens to the hydrogen protons in your body. The scanner's powerful field overpowers their random state and forces them to line up.
Now for Step 2, excitation. Okay, so all our protons are neatly aligned. The scanner then sends in a quick, carefully timed burst of radio waves. We call this a radio frequency, or RF pulse. This pulse is tuned to the perfect frequency for the protons to absorb its energy. And that jolt of energy is just enough to knock them out of alignment, flipping them into a new, high-energy orientation in what we call the transverse plane. And finally, we get to step 3, relaxation. The second that RF pulse is turned off, the protons are left in this unstable, high-energy state. And, nature doesn't like that. They naturally want to go back to their comfortable, low-energy alignment with the main magnet. To do that, they have to release the extra energy they soaked up from the RF pulse. And here's the magic. That released energy is the MRI signal. It's a very faint radio wave that the scanner's sensitive coils are built to pick up.
And this, right here, is the most crucial point of the entire process. Not all protons relax at the same speed. A proton in your spinal fluid relaxes at a different rate than one in your fat, which is different again from one in your brain's white matter. This difference in how fast they release their energy, the specific speed of relaxation, is what lets us tell the difference between tissues. It is the absolute, fundamental source of contrast in every single MRI image.
So that idea of relaxation brings us right to section 4, T1 and T2 relaxation times, because it turns out that relaxing isn't just one simple thing. It's actually two different processes happening at the same time, and understanding both is the key to really unlocking what MRI can do. First up, we have T1 relaxation, which is also called longitudinal relaxation. T1 is basically a measurement of how quickly the protons give up their energy and get back in line with the main, powerful magnetic field. So you can think of T1 as how fast the protons stand back up after being knocked over by that RF pulse. At the same time, we have T2 relaxation or transverse relaxation. See, the RF pulse doesn't just knock the protons over, it also gets them all spinning in sync or in phase. T2 relaxation is all about how quickly they lose that beautiful synchrony. Imagine a group of synchronized swimmers starting in perfect harmony. Inevitably, small differences cause them to drift out of sync. That loss of coherence, that's what we call dephasing.
This slide shows you exactly what we're talking about with T2 dephasing. On the left, right after that RF pulse, all the protons are spinning together, perfectly in phase. But then look at the right. Because of tiny little differences in the magnetic fields around them, they quickly lose that rhythm. And as they fall out of sync and dephase, the signal they were generating together starts to decay. The rate of that decay is what we measure as T2 relaxation.
Okay, so we have these two different relaxation processes, T1 and T2, and they happen at unique speeds in every different type of tissue. So how do we actually use that physics to create the pictures doctors look at? Well, that brings us to our final section, section 5, T1 versus T2 weighted images.
The real genius of MRI is how flexible it is. By very precisely adjusting the timing of those RF pulses, and when we listen for the signal, we can actually create weighted images. We can essentially tell the scanner, hey, for this picture, I want you to be more sensitive to T1 differences, or now I want you to focus on the T2 differences. This gives us different images that highlight different things.
And this weighting completely changes what the final image looks like. For brain scans, here's a simple little trick to remember the difference. On a T1 weighted image, tissues that relax fast in T1, like the fatty tissue and white matter, show up as bright. But on a T2 weighted image, things that take a long time to dephase, like water, for example, in the cerebrospinal fluid or CSF, those appear bright. So just remember, T1, fat is bright. T2, water is bright. So let's see how this actually plays out in a hospital. If a doctor wants to see the incredible details of the brain's structure, all the beautiful folds of the cortex, they'll use a T1 weighted scan. It gives you amazing contrast for anatomy, and the white matter really pops. But if they're hunting for signs of disease, like a tumor or a stroke or inflammation, things that often involve extra water, they'll turn to a T2 weighted scan. On that scan, the problem area with all that fluid will just glow like a beacon. And here's the final result. And it's why both of these scans are so important. On the left, you've got the T1 weighted image. It's like a crisp anatomical map. You can clearly see the brighter white matter from the darker gray matter. Then, on the right, that's a T2 weighted image of the exact same slice of the brain. But look how the fluid-filled spaces, the ventricles, with all that CSF, are now intensely bright. By comparing these two images, a radiologist gets a complete picture of that brain's health, seeing both the structure and any signs of disease. So we'll end with this question to think about. We've established that every single tissue in your body has its own unique T1 and T2 signature. So the question becomes, how can we push this technology even further? How could we use these specific signatures to detect the tiniest, most subtle changes in a tissue that might signal the very beginning of a disease, way before you could ever see it otherwise?
The future of MRI lies in decoding these subtle whispers of disease before they ever become a shout.